Welcome to this quick video about Physical Environment of Architecture, a course lectured by Professor Tsai in the NCKU Architecture Department. Today, we will be looking into some aspects of the light environment. Today, we'll first quickly overview the subject, then go into the environmental impact of lighting, as to know why lighting is important, and then provide some methods and tools for evaluation. Here are some key points we will touch on in this overview. Lighting can be grouped into two categories. Daylighting, which uses wholly natural sources of illumination, or artificial lighting, defined as any light source that is not naturally occurring. So that would be the light bulbs, lamps that we are very accustomed to in our building environments today. On the basic characteristics of light, apart from the very intuitive characteristic providing illumination, many properties of light come from a spectrum which we cannot see, ultraviolet rays. While overexposure to UV rays are a potential health hazard, they do play important roles in killing germs and are a vital actor in the production of vitamin D. On the right, we have a chart showing how many minutes of midday summer sun is needed for adequate vitamin D. So we can see that a certain amount of exposure to daylight is actually vital for the human body. When evaluating the performance of lighting, there are two main aspects: energy efficiency and visual effect. Due to its energy-saving capabilities, daylighting has become a major trend in the era of sustainability, even having a specific award called the Daylight Award for relevant building projects and research. However, it has always been a favorite topic of architects over the ages due to its outstanding visual effects and the way it can create the aura of a building. Here we can see the famous architect Stephen Hall naming light as his favorite building material. Environmental impacts of lighting includes both physical and psychological aspects. There's a specific area on this topic called environmental psychology, which investigates how the environment impacts place identity, your attachment to and sense of a place, cognition, and eventually your behavior. First, the physical aspects. Here is a quick overview of what we'll be talking about. When we look into the physical aspect of light, we can see it is distributed across a spectrum. Different wavelengths and frequencies have different properties and thus are used in different scenarios. The visual spectrum refers to the range of wavelengths that can be detected by the cones and rods on the retina of the human eye. Cone cells detect color, and rods have higher accuracy in lower light situations, thus are mainly used in night vision. This results in an adaptation process when transferring from light to dark or dark to light, as shown on the right, which is called light-dark adaptation. Apart from the visible spectrum, we also have different uses of UV light according to penetration and energy levels. UV can be categorized into UVA, UVB, UVC. Normally, UVC is used in building environments for germicidal irradiation in labs or sanitary spaces, or used in AC systems or air cleaning devices. Apart from the inherent properties of light, we will also introduce some physical phenomena occurring in the human body. First, the Weber-Fechner law that describes the logarithmic relationship between sensation magnitude and stimulus intensity. The law states that when stimulus intensity exceeds the absolute threshold level, meaning it has reached a magnitude that is perceptible to senses in the body, subjective sensation magnitude and stimulus intensity share a logarithmic relationship. This means that even though the stimulus intensity increases linearly, the sensation magnitude will increase exponentially. In plain words, This means that a slight increase in stimuli will result in a very, very big difference in how you feel. However, when the stimulus, in this case we will be talking about light, exceeds the maximum threshold, so when the light is overly bright, it is not only rendered ineffective, it also causes discomfort and pain, or in some cases, it even causes irreparable damage. Next, we have the Purkinje effect. The Purkinje effect describes the phenomenon where colors take on a bluish tone in lower light. To put it in more academic jargon, it is the tendency for the peak luminance sensitivity of the light to shift towards the blue end of the color spectrum at low illumination levels as a part of dark adaptation. Next, we move on to the psychological effect of lighting, touching on visual comfort and arousal. First, how light color influences visual comfort. Here we have an example. An elder using white light feels that it is harsh on the eyes and feels much more at ease after changing to a yellow light bulb. Why is that so? That is because accumulated proteins cause cataracts in the elderly, causing a scattering of short wavelength blue light. A second example. Professional dessert bakers join an experiment with the objective of judging sweetness levels. Under white light, these bakers can detect slight differences of sweetness levels, but become duller and worse at detecting such differences under red or yellow lighting. This is because, opposed to red or yellow light, the color of white light raises sensitivity towards sweetness and bitterness, while yellow light increases gastric movement. So we can see that light color is very linked to visual comfort. Next, light color and arousal. First, we will share a sleeping experiment. 20 lab rats divided into two groups, one sleeping with white light and the other with yellow light. Results show that the yellow light group had better sleep quality. Through further research, we can see that the same applies for humans, who also show better and deeper sleep when exposed to yellow light prior to sleep. This is something that you may have often heard of, as shown as a picture on the right. When exposed to blue or green light before sleep, such as when you're late night doom scrolling, the exposure to light with a wavelength between 460 to 555 nanometers inhibits melatonin secretion and causes difficulty falling asleep. On the other hand, morning light triggers secretion of serotonin, causing wakefulness. So from the above four examples, we can see how lighting can have a very big impact on our daily lives and thus is a pretty important factor when designing spaces. Now that we understand the importance of lighting, let's explore some objective tools to aid our building designs. The most basic tool for light analysis in architecture is a sun path chart, which shows where the sun will be in the sky at any time and date of a specific location. Here are two websites for making sun path charts that you can check out after this video. Here are some basic units of light we need to know to be able to understand the lighting indexes that we will be mentioning later in the video. First, originating from the Latin word fluxus, meaning flow. Flux is the amount of energy a light emits per second and measured in lumens. You can see the units used in the parentheses alongside. Illuminance, the second unit of light, is the amount of luminous flux per unit area. Lux is a standardized unit of measurement of the light intensity. 1 lux is equal to 1 lumen per square meter. Luminance is the intensity of light from a surface per unit area in a given direction. We measure luminance per square meter in nits. For an easy understanding of this concept, think of a lamp that produces light. The light from a lamp is measured in lumens, the measurement of light intensity. The light that falls on the surface, as seen in the blue surface on the left little image, is expressed as lux. The human eye sees this visually in terms of brightness or luminance that is measured in candelas, the middle part of the image on the left. The amount of candela per square meter is nit. Here we can see some standard values of lighting for given activities. When designing a building or spaces for specific activities, we can come to this chart and determine if the lighting is satisfactory for that task at hand. Now, let's learn some indexes to use in evaluating artificial lighting and daylighting. Have you ever been in a situation where it's so bright that you cannot see a thing? That's clear. It's defined as the ratio of the luminous intensity of the background to the luminous intensity of the light source. Unified Glare Rating, UGR, is a calculation method of glare recommended by the International Commission on Illumination, CIE. The formula considers luminous intensity of the background, luminous intensity and positioning of the light source to predict glare that may cause discomfort in the environment. Uniformity of illuminance is used to describe how evenly light is distributed in the visual task area. There are 2 evaluation formulas as shown in the lower right corner. However, we normally use the first one, the quotient E minimum over E average of the minimum and average illuminance in the visual task area. When the value of illuminance is too low, which means that the uniformity is low, the environment causes fatigue. Now we move on to indexes used in evaluating daylight. We can see the formula of daylight factor is listed, where IN refers to illuminance due to daylight on the indoor working plane, and I out refers to illuminance outdoors on an unobstructed horizontal plane. The quotient of I in divided by I out, then multiplied by 100%, should equal 2%, which means though the natural light source is constantly fluctuating, there will be a minimum of daylight at any point in the day to provide adequate lighting for daily use. On the lower right side is a small excerpt from Greg D. Anders' research if you would like to know a bit more about this. Here we have 2 charts which show the appearance and energy implications of different DF values. When the daylight factor is lesser than 2%, we need artificial lighting and the room looks gloomy. When DF is above 5%, however, the room is very brightly lit but has potential thermal issues. It could be too hot, and which would use up more energy. The chart on the right side provides information on daylight factors and standard values for lighting for different tasks. You should be able to find more information at the blogspot shown on this side. Finally, we will be introducing daylight index. We have already introduced the indexes used in static daylight analysis. However, daylight fluctuates, meaning we need a better method of evaluation, thus resulting in the appearance of dynamic daylight analysis, or also called climate-based daylight metrics. We will be introducing 4 dynamic indexes today. The first is daylight autonomy, which refers to a percentage of annual daytime hours that a given point in space is above a minimum illumination threshold, approximately could be about 300 lux. This basically means the percentage of time where lighting conditions are adequate without the need of additional electrical and artificial lighting. The next index is the useful daylight illumination, UDI, which is basically the same. However, referring to the percentage of time that the space is in a useful illumination range using daylighting alone. You could cross-reference the aforementioned standard value of lighting chart to see what values of illumination are suited for each task. Spatial daylight autonomy, SDA, which is kind of like daylight autonomy, but where DA evaluates using time, SDA looks at the percentage of space that reaches a certain illumination threshold, say 300 lux, for a certain proportion of time, for example 50%. So to make that a bit clearer, when using DA, I might say that the whole building has a DA of 50%, meaning out of the 12 hours I use the building, 6 can operate on daylight alone. If using SDA to evaluate that same building project, 50% SDA means half of my space can operate on daylight alone for 6 hours a day. So SDA is a kind of more precise way of evaluation in some way. Annual sunlight exposure, on the other hand, does not inspect whether your building is receiving enough daylight. It inspects whether a building receives too much daylight, resulting in energy waste. Same as SDA, this evaluation is based on a proportion of space, of floor area. Using the same example as previously, 50% ASE, so 50% of annual sunlight exposure would mean that half of my building floor area receives way too much direct sun, and thus my design team should work on design methods to reduce that area in order to save energy and also create a more comfortable environment. Lastly, dynamic daylight analysis or climate-based daylight metrics are used for LEEDS, which is a green building rating system. Quick summary. Today we had a quick intro to lighting, then introduced environmental impacts of lighting, touching on the physical and psychological. Then we learned some tools for analysis and gave you websites to create sun path charts. Lastly, we introduced the current criteria for lighting analysis, where we learned a lot of indexes to use, such as UGR, UI, DF, etc. I hope this helped with your studies or design project. Please have a nice day.